Today's topic is network theorems. In these network theorems, we are going for Thevenin's, Norton's, and compensation theorem. So first come to the Thevenin's theorem. So the statement of Thevenin's theorem is any two-terminal network is replaced by a single voltage source in series with single impedance. The single voltage source must be considered as a terminal at the load is open circuited and measure the voltage between the points. So that is also called open circuit voltage or Thevenin's voltage. And while we are coming to the Thevenin's impedance, wherever the sources are there, make the values are zero. So that means voltage source is made zero means short circuited, and current source is made zero means open circuited, and replace with their internal impedances and measure the Thevenin's impedance between the points. So here I instructed an example. So it is a two-terminal network. So the two-terminal network is connected to a particular load with an impedance of ZL, and the load current is IL. So now I am open circuiting the load and I am measuring the Thevenin's voltage or open circuit voltage, and also I am measuring the Thevenin's impedance. Then this entire network is replaced by a single voltage source in series with the impedance, and this network is connected to your load. Then after connecting this, so A and C are joined, B and D are joined, so the current IL will flow through the circuit. So the load current can be represented as VOC or VTH divided by ZTH plus ZL. So this is the total load current we are calculating, the response at a particular load for an entire complexity of the network is replaced with a single voltage source in series with a single impedance. Okay. So come to the limitations and applications of the Thevenin's theorem. So it is not applicable to the circuits that contains non-linearity and time invariant elements, so such as transistors, diodes, and etc. And also, so this theorem is not applicable for the magnetically coupled between the load and any other circuit elements, between the load and any other circuit elements. At that time also this theorem is not applicable, and there is no provision for calculation of Thevenin's equivalent circuit when the load contains with a series and parallel with controlled or dependent sources. So such a type of networks, so you cannot go for the application of a Thevenin's theorem. So these are the limitations. And while we are coming to the applications of the Thevenin's theorem, so the complexity of the network will be replaced with a single voltage source with a single impedance or a resistance. So that means the entire network you are reducing into a very lumped circuit. So it is very lumped circuit. And second thing is, once the Thevenin's equivalent circuit is calculated, you can go for the maximum power transfer theorem also. So with respect to any complexity of the network, if you reduce the entire network by using Thevenin's theorem, and you can go for further calculations with the power with the maximum power transfer theorem for power calculations. So these are the applications of the Thevenin's, and there are lot of applications involved in electrical circuits, at the same time in power systems also. So any outages are there, entire the circuit is replaced with a single voltage source in series with the single impedance. Then you are calculating the voltages According to that, you are regaining the systems. So such applications are you are studying further. Next, coming to Norton's theorem. So Norton's theorem is a source transformation of Thevenin's theorem only. So the statement of Norton's theorem is the electrical network carries with active and bilateral linearity networks with a two-terminal network. So the two-terminal network is replaced with a single voltage source in series in parallel with the impedance. So this is a network. So for this network, the load is connected between the terminals A and B. The load current is IL. So the load is open circuited. So you are calculating the short circuit current between the points A and B. The short circuit current is also called Norton's current, and whatever the Thevenin's impedance you are calculating between the points A and B, the same as Norton's impedance also, Zn. And the entire network is replaced with a single current source in parallel with the Thevenin's impedance or a Norton's impedance. So this is connected to the load. Once you are connected to the load by using the current division method, so IL is equal to total current IS into opposite impedance Zn divided by Zn plus Zl. So you can calculate the response of a particular load for a complexity of the network by reducing with the Norton's theorem. Okay. So now the limitations for Thevenin's and Norton's must be same. There is no any alternation because it is just a source transformation. Voltage in series with the impedance is current in parallel with the same impedance. So this is the simple concept of source transformation. Voltage in series with the resistance must be same as a resistance and a source current of V by R. So resistance must be same either in the voltage connected in series or current connected in parallel. That is the most important thing. Okay. So come to the numerical problem. So Thevenin's. So here you are going for the voltage drop across the 100 ohm resistor. So let us assume between the terminals A and B is a load. The load resistance is 100 ohms. We have to go for the calculation of the 100 ohm resistor voltage drop. Okay, by using Thevenin's equivalent circuit. So for this one, first case is for finding the Thevenin's equivalent circuit. You have to open circuit the load. You have to measure the voltage between the points. Second step is wherever the voltage sources or current sources are there, made zero and replace with the internal impedance and calculate the impedance between the points. Wherever the load is open circuited, between those two terminals only you have to measure the impedance. That is RTH you can get. So once you are getting the RTH and VTH, then the voltage source connected with series resistance is connected to the load terminals, then you can calculate the load current. But while you are going to the dependent sources, so here for the problem 86 volts is a independent source, but 6 is is a dependent source. So at that time we have to go for one thing is assumption of current at the open circuited points. So with respect to that, you can go for the calculation of VTH and you have to go for the calculation of RTH also. Or we have to short circuit the points and you can measure the short circuit current. Then RTH is VTH divided by ISC, short circuit current. VTH is the Thevenin's equivalent voltage. Okay. So now between the points you are calculating. So this value VAB is same as VOC is same as VTH only. So I am going for the application of KVL in this loop. So here minus 86 plus 50 plus 30, 80 is 80 is plus 6 is equal to 0. So from this you can get is is equal to 1 ampere. So now what is VOC? VOC is the voltage drop across this element. The voltage drop across this element. So that is 6 is plus 30 is. So finally you can get that voltage is 36 volts. Are you understanding? So next, here I told, so for a independent sources, so voltage source must be short circuited, so the dependent source must be activated and the load is open circuited, so there is no current flowing through the circuit in case of a general circuits, but here a voltage current controlled voltage source is there, so you cannot directly calculate. So let us assume a 1 ampere current source. So with respect to that I am calculating the currents. Once I have calculated the currents, then you can go for the calculation of the voltages, then you can calculate the RTH value. So here 30 is, so 30 is the 50 is the voltage drop across 50 ohms. So 30 into is plus 1, so it is the voltage drop across 30 ohms, and 6 is a current controlled voltage source. So if you substitute 0, so from which is is equal to minus 15 by 43 amperes you are getting, minus 15 by 43 amperes you are getting. So for the left loop, while you are coming to the right loop, so the total voltage drop here it is 50 into is minus 15 divided by 43 minus 1 into 40 is the voltage drop across the 40 ohms, and V is the current source voltage is equal to 0. So from this you can calculate the value of V. So how much you are getting? 57.4 volts. Then RTH is equal to V by I. So that is equal to 57.4 ohms. So once you are calculated the RTH, already you are calculated the VTH, then the equivalent circuit is 36 volts is the VTH value, 57.4 ohms is the RTH value, and your load is 100 ohms. So then V100 is equal to apply the voltage division. So total voltage 36 into same resistance 100 divided by the resistors those who are connected in parallel. So 57.4 plus 100. So finally you can get 22.9 volts. So like this you have to solve the problem of dependent sources using Thevenin's theorem. Next, coming to the next problem. So here we are going for the calculation of voltage drop across x to y. Voltage drop across x to y. So here 100 volts is a independent source. 10 into ix is a dependent voltage source. So ix is the current flowing through 60 ohm resistor. Okay. So for finding the value of RTH, so wherever the load is there, you have to open circuit the load and you have to measure the Thevenin's equivalent resistance. But here, due to the voltage controlled current source, so I am assuming 1 ampere is the current source, and across the 1 ampere the voltage is V volts. So by using this equivalent circuit, I am going for the calculation of RTH. So 1 ampere is coming here. So Ix is moving like this. So here it is 1 minus Ix current. So 3 currents are there. So with respect to that, so we are going for writing the expression minus 50 into 1 minus Ix voltage drop across the 50 ohms. So 10 into Ix is the voltage controlled voltage source, current controlled voltage source, minus 20 into 1 minus Ix is the voltage drop across the 20 ohms. So 60 into Ix is the voltage drop across the 60 ohms. So finally Ix is the variable, so you can get 0.5 amperes. 0.5 amperes. Next, coming to the right hand side, so 60 into Ix, so with minus sign, so Ix value is 0.5, so minus 60 into 0.5 minus, so 1 ampere into 20 is the voltage drop across the 20 ohm resistor. So voltage drop across the current source is V. So here V is the unknown value. So finally you can get V is equal to 50 volts. So now the Thevenin's equivalence resistance is 50 ohms. So already 50 ohms is there. He is connected with a voltage of 100 volts. So finally the voltage drop across Vx is 50 volts only, because two resistors with same values. So like this you have to go for the calculation of Thevenin's theorem problems. Next, coming to the another problem. So here two independent sources are there and one dependent source is there. So it is a voltage controlled voltage source. So you are going for the Thevenin's theorem for finding the value of I. So that is current flowing through 2 ohm resistor. So let us assume the 2 ohm resistor is a load. So for finding the value of VTH, we have to open circuit the load and we have to measure the voltage. So first case. Second case is we have to remove all voltage sources or current sources with their internal impedances, and you have to measure the voltages. You have to measure the equivalent resistance value. So now we are going for the first case. So that is load is open circuited. I have taken the total loop current like this. So in this clockwise direction. So VOC is the open circuit voltage, is same as the VTH. So 10 volts is applying, 1 ampere is also applying. So from this I am writing the expression for KVL. So minus 10 minus V naught plus 3 times of V naught plus VOC is equal to 0. So total algebraic sum of the voltages is equal to 0. So from this VOC is equal to 10 minus 2 V naught you are getting from the above equation. So now this dependent source will be there. So you cannot directly calculate. So that's why we are assuming between X and Y with 1 ampere current source. 1 ampere current source. So for this 1 ampere current source, what is V naught? What is V naught value? So that is you can get as 1 volt only, because V naught is the potential between the two nodes. So is same as 1 only. So 1 volt. So if you substitute, you can get VOC is equal to 10 minus 2, that is equal to 8 volts. So that is the open circuit voltage or Thevenin's equivalent voltage. Next, coming to the KVL for the loop for finding the RTH. So the total loop, so minus 10 minus V naught plus 3 V naught is equal to 0. So V naught is equal to how much you are getting? 5 using the above equation. Then apply the nodal analysis at node A. So V naught by 1. So here 3 currents are there. So V naught by 1 is equal to 1 ampere is entering, ISC short circuit current is leaving, so 1 minus IS. So IS is equal to 1 minus V naught. So V naught is 5. So finally you can get minus 4 amperes. So once you calculated the ISC value, you calculated the VTH value or a VOC value, then you can get RTH is equal to VOC or VTH divided by ISC, short circuit current. So 8 by 4. So finally you can get 2 ohms. You can get 2 ohms. Next, coming to the another numerical example. So here you are going for the Thevenin's equivalent circuit for the given circuit shown in figure A. So for this figure A, so you are having one independent voltage source and another one is current controlled current source. So 9I is the current controlled current source, 6 volts is the independent voltage source, that is also denoted as source voltage. So now the current I is the current flowing through 20 ohm resistor. So once the load is open circuited between the terminals A and B and the open circuit voltage is VOC, so at the node A, so the current you are getting as Vs minus VOC divided by 80 plus 20. So net resistance is 80 plus 20. So Vs minus VOC is the net voltage. So you can get the value is 6 minus VOC divided by 100. So because Vs is 6 only. Okay. Then apply the KVL at node A. So 6 minus VOC divided by 100, it is the first branch current. 9I is the second branch current. And what is I? I is 6 minus VOC by 100. So 9 into 6 minus VOC by 100, it is the second current. And the third current is VOC by 10. So VOC by 10 with minus sign is equal to 0, is equal to 0. Then the final value of VOC is 3 volts. 3 volts. So next, for finding the RTH, so here I am assuming a 1 ampere current source. The voltage drop across the 1 ampere current source is VAB. So VAB is same as VTH only. VAB is same as VTH only. So with respect to that, I am going for the calculation. So here also 4 branches are connected in parallel. So 1 ampere current source is flowing. So another one, the 9I current source is flowing. So 80 plus 20 is the voltage, is the resistance, total resistance value is parallel with the 10 ohm resistor. So in this case also, I am calculating the current of I. I is the 20 ohms resistor current. So how much we are getting? So it is the same expression. So I is equal to Vs minus VOC divided by 100. Here the Vs value is 0. So finally you can get minus VOC divided by 100. So that is the I value you are getting. So from this, the 4 branch currents you are writing. 4 branch currents you are writing. So how you are writing? The first one is minus VAB divided by 100 plus 9I. So what is I value? Minus VAB divided by 100 minus VAB divided by 10 plus 1 ampere current source 1 is equal to 0. So from this you are getting VAB is equal to 5 volts. So RTH is equal to 5 divided by what is the current value? 1 you are assumed. So 5 by 1, so 5 ohms. So finally VTH in series with the RTH is the Thevenin's equivalent circuit. So 3 volts is series with 5 ohm resistor. So like this you have to calculate the equivalent circuit by using Thevenin's theorem. So next, another example. So in this example also, one current source one voltage source. These two are independent sources. So another one is a voltage controlled voltage source, that value is V by 3. So where V is the voltage across 15 ohm resistor. So in this circuit also, the question is equivalent representation of Thevenin circuit they are asking with the application of Thevenin's theorem. With the application of Thevenin's theorem. So here whatever the voltage drop across 50 ohms is V is same as the node voltage or between the points VAB. Between the points VAB. So that's why V is same as VAB only. So now you are having three currents. So this is one current, this is another current, this is another current. So 30 ohms is open circuited, no current will flow through the circuit. So finally three currents are there. The algebraic sum of the three currents must be equal to 0 according to Kirchhoff's current law. So the first current you are writing as minus 5. So 5 amperes is leaving away. So minus 5. The second current is minus VAB by 15. So this is the current flowing through 15 ohm resistor. And the third current is total resistance is 1 by 10 and the total current is VAB by 3 plus 150 minus VAB. So because V is same as VAB, we are substituting this value. So finally one unknown value. So one equation. So finally you can get VAB is equal to 75 volts. Next, while finding the RTH, so it is a dependent source is there. Current source is open circuited. So I am assuming a 1 ampere current source with a voltage drop of VAB. With a voltage drop of VAB. So now at the node A, so VAB minus 30I. VAB minus 30I. So that is the value is same as V only. Is same as V only. So now I is equal to, so you are writing VAB minus 30I divided by 15. So I is equal to VAB divided by VAB minus 30I divided by 15 plus 1 by 10 VAB minus 30I divided by 3 minus VAB minus 30I. So the net current here, it is flowing through 10 ohm resistor will be VAB minus 30I divided by 3 minus VAB minus 30I divided by total 10. So finally net current values must be equal to 0. So you can get the value of voltage final expression will be 4 VAB is equal to 150I. 4 VAB is equal to 150I, and already VAB is 75. Then you can calculate the current value. After that RTH is equal to VAB divided by I. Finally you can get 75 by 2 ohms. So the Thevenin's equivalent circuit is a voltage source in series with the resistance. The voltage source value is VTH is equal to 75 volts and the RTH value is 75 by 2 ohms. So like this you have to go for the Thevenin's problems. Next. So another circuit, they are given 4 ohms is a load. So for this load we have to go for the equivalent circuit. For the given circuit, one is a dependent source, another one is a variable source. So that is independent source. So 10 volts is a independent source. 4 V6 is a dependent source. Okay. So now for finding this, I am going for the open circuiting of the 4 ohm resistor. Then I am going for the Kirchhoff's current law. So the value we are getting is VOC minus 10 divided by 2 is equal to 4 V8. So that is equal to 4 into 10 minus VOC. 4 into 10 minus VOC. So from that finally you can get VOC is equal to 10. So here see this. So 4V8 must be same as 4 times of 10 minus VOC. So VOC is the potential voltage. VOC is the potential voltage. 10 volts is the voltage source. So 4 times of 10 minus VOC is the value which is across this 4 times of V8. So from that, by substituting, you can get VOC. Thevenin's equivalent voltage is 10 volts. Then I am short circuiting the load, and the short circuit current is ISC. So I am going for the application of Kirchhoff's current law. So node voltage I am considered as V1. So V1 minus 10 divided by 2 plus V1 by 4. V1 by 4. So this current, and what is this current? 4 V8 is the another current. So from this also the same thing, 4 times of 10 minus V1. So VOC is same as V1 only. Across the potential is V1 only. So 10 minus V1. So now you can get V1 is equal to 180 divided by 19 or 9.47 volts. Once you calculated the V1, so the short circuit current ISC is equal to 9.47 divided by 4. So 2.368 amperes. Then RTH value, RTH is equal to VOC divided by ISC or VTH divided by ISC. So you can get 4.2 ohms. 4.2 ohms. Okay. Another example of Thevenin's circuit. So here a current source is there which is independent, and a voltage controlled voltage source is there. So 4 ohm voltage drop is Vx only. So we are going for the equivalent circuit of the Thevenin's circuit of the given circuit. So the first case for finding the RTH, I am replacing the current sources must be equal to 0. So it is open circuited. So now this is the equivalent circuit. So for this equivalent circuit, so it is also represented here. For this equivalent circuit, so I am writing the KVL for the loops. So the first loop I1, so here we are calculating the loop 1. So minus 2 Vx plus 2 times of I1 minus I2 is equal to 0. So voltage controlled voltage source plus drop across the 2 ohm resistor, 2 times of I1 minus I2 is equal to 0. So finally Vx is equal to I1 minus I2. So another equation here. So minus 4 times of I2. Minus 4 times of I2 is voltage drop across 4 ohm resistor only. So what is that value? Vx. And what is Vx? Vx is I1 minus I2. So finally the correlation with I1 and I2 is I1 is equal to minus 3 times of I2. Minus 3 times of I2. So now using the second loop and third loops. So what is your second loop? Minus 4 times of I2 plus 2 times of I2 minus I1 plus 6 times of I2 minus I3 is equal to 0. And your third loop is 6 times of I3 minus I2, 2 times of I3 plus 1 is equal to 0. So these are the two equations you are getting. So by using this, if you solve the equations, so I0 is equal to minus I3 is equal to 1 by 6. So I0 is the equivalent current I am calculating. Okay. So from that RTH is equal to V0 divided by I0. So V naught I am assumed as 1 volt. So 1 volt divided by 1 by 6. So finally you can get RTH is equal to 6 ohms. So next, for finding the value of VTH, so wherever the load is there, we have to open circuit and we have to measure the Thevenin's equivalent voltage. So here also 3 loops are there. For finding the VOC, you required I2. So the first loop I1, so I1 current is same direction of 5 amperes. So I1 is equal to 5 amperes. The second loop is minus 2 Vx plus 2 into I3 minus I2. So that is your second equation. So from this Vx is equal to I3 minus I2. Then the third loop equation is 4 times of I2 minus I1 plus 2 times of I2 minus I3 plus 6 times of I2 is equal to 0. So from this, after reduction, so we are getting as 4 into I1 minus I3 is equal to Vx. So equation 1, equation 2, equation 3, equation 4, if you solve, you can get I2 value is 10 by 3. So VTH value is VOC, that is equal to 6 times of I2. So that is equal to 2 volts. Whatever the voltage drop between the points is 6 ohm with respect to that current. So 6 times of I2. So finally you can get 20. So Thevenin's resistance value is 6 ohms. Thevenin's voltage value is 20 ohms. This is your equivalent circuit. Next. Now I am going for the examples of Norton's theorem. So this is a circuit they are given. So you have to go for the equivalent circuit using Norton's theorem. So the Norton's equivalent circuit we are calculating. So first for finding the RTH, so here one independent source is there, two dependent sources are there. 5 volts is an independent source. So 3 Vx, it is a voltage controlled voltage source, and 25 Is, it is a current controlled current source. So Vx is voltage drop across the 20 ohm resistor. Is is the current flowing through 1000 ohms. So now I am writing the expression for VOC. So this is the open circuit voltage. So VOC is same as Vx. So here these two terminals, no current is flowing. So the total current is flowing in the 40 ohm resistor only. The voltage drop across 40 ohm resistor Vx is 25 Is with minus sign into 40. So finally you can get minus 1000 Is. For next case, I am assuming the short circuit current. So this is the short circuit between the terminals. So 3 branches are connected in parallel. So here the ISC value are calculating. So the ISC value is same as 25 Is with negative sign, because 40 ohms is directly shorted, so no current will flow through this branch. So whatever the current flowing must be in the short circuit line only. What is that value? Minus 25 Is. So Rn is equal to VOC divided by ISC minus 1000 ISC divided by minus 25 ISC. You can get 4 ohms. 40 ohms. You can get 40 ohms. So next, for finding the Norton's current. So wherever the load is there, you have to open circuit. So I am writing the KVL equation in the left loop. So that is minus 5 plus 1K. 1K means 1000. What is that current? Is. So 1K into Is plus 3 times of Vx. So what is Vx? Vx is minus 1000 times of Is. So 3 into minus 1000 times of Is is equal to 0. So from that, the current we are getting is minus 2.5 milliamperes. So now short circuit current is equal to minus 25 times of Is. So substitute the Is value here. So the short circuit or Norton's current is 62.5 milliamperes. So this is your Thevenin's equivalent circuit, Norton's equivalent circuit. So where the total circuit is replaced with single current source in parallel with the single resistance. Next problem. So in this problem, so we have to go for the current value IB and the load resistance is 667 ohms. 667 ohms. So using Norton's equivalent circuit. Using Norton's equivalent circuit. So here the load is open circuited as shown in the figure 3.70. So in this case, the source one is a independent, another one is a dependent. So dependent source is a current controlled voltage source. Okay. So the first IA value. So IA value here, the terminals are open circuited. So finally it is 0 amperes only. Then ISC value. So what is your ISC value? So ISC value is 20 divided by 6000. Sorry, 12 divided by 6000. So why? Because the IA value is the current flowing through this 1000 ohm resistor. This 1000 ohm resistor, it is directly short circuited. No current will flow through this circuit. So no current will flow to the circuit. So finally the ISC value is 12 divided by 6000. So you can get 2 milliamperes. 2 milliamperes. For finding the Rn, so Rn value is VOC divided by ISC. So right hand side I am writing the loop equation. So minus 12 plus 6000 IA plus 2000 Ia plus 1000 Ia is equal to 0. So from this Ia is equal to 4 divided by 3000. So finally VOC is equal to Ia into 1000. So we can get 4 by 3 volts. So Rn is equal to, so VOC divided by ISC, you can get 667 ohms. 667 ohms. So now equivalent Norton's current. So equivalent resistance is connected in parallel with the load. So load resistance and Thevenin's equivalent resistance both are same. So the net current is half of the value. So that is 1 ampere only. 1 milliampere only. So next, coming to the another example. So here also we are going for the Norton's equivalent circuit for the given circuit A. So for this circuit, so VAB is open circuited voltage. So I is the current. I is the current. So this current is flowing through 200 ohm resistor. The net voltage is 2 volts. So I is equal to 2 by 200. So that is 0.01 amperes. Then the short circuit current. The short circuit current shown in figure B, ISH. So ISH is a short circuit current, is directly shorted the 20 ohm resistor. So no current will flow to the 20 ohm resistor. So finally minus 5 times of I. So what is I? I is 0.01. So finally you can get minus 0.05 amperes. So next, writing in the left hand loop, so 2 minus 200i minus VAB is equal to 0. So this value you are writing. So 2 minus 200i minus VAB is equal to 0. So in this case, so VAB value, so the VAB value we are calculating, the I value we are writing as minus VB by 100. So because VB or VAB must be the node voltage. So what is the current? Voltage divided by resistance. So that value is minus VB VAB divided by 100. So by substituting, finally you can get one unknown. So that is VAB is equal to minus 2 volts. Once you are getting the current and voltage, then Rn. So Rn is equal to VAB divided by ISH. So that is equal to, so minus 2 divided by minus 0.05. So you can get 40 ohms. So then the equivalent current source in parallel with the resistance is the Norton's equivalent circuit. So in this example, they are asking to find the Norton's equivalent circuit. Here you don't have any independent sources, only dependent source is there. So the dependent source is a voltage controlled current source. So which voltage? This 100 ohm resistor voltage controlled current source. Okay. So for finding the value of RTH, so you have to assume a 1 ampere current source is connected between the terminals A and B. So by using that, so here two currents are there, and two resistors are connected in parallel. So let us assume that first node voltage is V1, the second node voltage is V2. So apply the Kirchhoff's current law at node 1. So node 1, you are having three currents. So 1 is equal to V1 by 100 plus V1 minus V2 by 50. So that is your first node equation. So by simplification, 0.03 V1 minus 0.02 V2 is equal to 1. Then coming to the second node, so here also three currents are there. So V2 by 200 plus V2 minus V1 by 50 plus 0.1 V1 is equal to 0. So after simplification, 0.08 V1 plus 0.025 V2 is equal to 0. So two equations, two unknowns, V1 and V2. So if you calculate, V1 is 10.64 volts and V2 is also 10.64 volts. Then Rn is equal to, or RTH is equal to VOC divided by ISC. So ISC value you are taken as 1 ampere. So 10.64 divided by 1. So you can get 10.64. So only Thevenin's resistance you can obtain for this circuit. So coming to the another example. So here two independent sources are there. One dependent source is there, 50 volts voltage source, 5 amperes current source, and the dependent source is 10 times of IA. So it is a current controlled voltage source. So I am going for the Norton's equivalent circuit and Thevenin's equivalent circuit using the given circuit. So the first loop equation is minus 50 plus 2 times of IA minus 20 plus 4 times of IA. So here the circuit B, I am taking the source transformation of this. The source transformation of the 5 amperes with 4 ohm connected in parallel. So by using that, I am calculating this. So IA value finally you are getting as 70/6 amperes. Then by applying the right hand side, so 20 plus 10 times of IA plus VOC minus 4 times of IA is equal to 0. So from this VOC is equal to minus 90 volts. So this is the first loop, first circuit equations and their values. So while you are coming to the second condition, so for finding the RTH, I am short circuiting the bit terminals A and B. So the short circuit current is ISC. So I am taking the loop currents IA and ISC. So now the left loop, so minus 50 plus 2 times of IA minus 20 plus 4 times of IA minus ISC is equal to 0. So finally you can get 6 IA minus 4 ISC is equal to 70. Then coming to the right hand side loop, so 4 times of ISC minus IA plus 20 plus 10 times of IA is equal to 0. So finally you can get 4 ISC plus 6 IA is equal to minus 20. So this is one equation, this is another equation, two equations, two unknowns. If you solve, so finally you can get ISC value is minus 11.25. So Rn or RTH is equal to VOC divided by ISC minus 90 divided by minus 11.25. So finally you can get 8 ohms. So VTH value is 90, RTH value is 8 ohms. This is the Thevenin's equivalent circuit. They are connected in series. So ISC value is 11.25 or 90/8 and 8 ohms is same as RTH value. They are connected in parallel. So this is Norton's equivalent circuit. So like that you can go for Thevenin's and Norton's for the same problem also. It is just a source transformation. It is just a source transformation. Are you understanding this, students? So next, coming to the one more example. So here a independent source 10 volts is there, a dependent source is there, a current controlled current source, so 2 times of Ix. So you are going for the Norton's equivalent circuit. So for going for Norton's equivalent circuit, here I am assuming a 1 volt is the voltage drop between the terminals A and B, between the terminals A and B. Okay, so here if it is open circuited, there is no current flowing through the circuit. So that means Ix is equal to 0. So that's why you cannot find anything. So now by adding this 1 volt voltage source, so you can go for the I0 value. So how you can get the I0 value? So I0 value is equal to 1 divided by 5. 1 divided by 5, so that is equal to 0.2 amperes. So because Ix is equal to 0. So now Rn is equal to V0 by I0, so that is equal to 1 divided by 0.2. So finally you can get 5 ohms. So next, short circuit the terminals A and B, so that is short circuit current or Norton current. So now we are going for the equation, the Kirchhoff's current law I am applying. So here the IN value is same as ISC, that is equal to 10/5 plus 2 Ix. So only two currents will be there. So only two currents will be there. So one is 10 divided by 5 plus 2 times of Ix. So already Ix value is how much? Already that Ix value is how much? You have to calculate the Ix. So how you can calculate the Ix? Ix is the current flowing through 4 ohm resistor. What is the voltage drop across 4 ohm resistor? 100 volts. So Ix is equal 10 volts. Ix is equal to 10 divided by 4, 2.5 amperes. So now the Norton's current is equal to 2 plus 2 into 2.5. Finally you can get 7 amperes. So now this is the Norton's equivalent circuit. So entire circuit is replaced with a single current source in parallel with the equivalent resistance. So the current source value is 7 amperes and the Norton's resistance value is 5 ohms. So now come to the compensation theorem. So the statement of compensation theorem is, in any linear active bilateral networks, so the branch current and branch impedance will flowing in a circuit. Suddenly there is a change in the increment of impedance. There is a change in the increment of impedance or increment of branch. At that time the increment of voltage will be there, the increment of current will be there. So such a condition, we are calculating the incremental voltage with respect to the given circuit is represented with compensation theorem. So to understand this, the modified compensation theorem is substitution theorem only. The modified compensation theorem is substitution theorem only. So to understand this, I am going for the simple example. So here a voltage source Vs, the impedance of voltage source is Sg and a load is Z. So now the total current I can be represented as Vs divided by Zg plus Z. Now there is any increment in the impedance. So let us assume the total impedance now it changes to Z plus delta Z. Z plus delta Z. So there must be increment in the current. So that current I am taking as I dash. That current I am taking as I dash. So now for this incremental impedance, instead of Z, we are taking Z plus delta Z. The incremental current value is Vs divided by Zg plus Z plus delta Z. So such a conditions are happened practically in any electrical networks. So at that time we have to compensate. So that's why this theorem is also called compensation theorem. So we are compensating and we are maintaining the currents with the same levels. We are maintaining the voltages with same voltages. Okay. So how it will be means, so the incremental current you are getting with respect to incremental impedance, you are taking the compensation voltage. So what is that compensation voltage? Vc is equal to I into Z with same polarity. Now for the second figure, due to the incremental thing, the new compensated voltage is Vc dash is equal to I dash into Z plus delta Z. Z plus delta Z. Now what is the difference? Differential current is equal to I plus I dash, that is equal to Vs by Zg plus Z minus Vs divided by Zg plus Z plus delta Z. So delta I, the final value you are getting as I delta Z divided by Zg plus Z plus delta Z. Zg plus Z plus delta Z. Okay. So this amount of incremental current will be there. So that difference you are compensating by using the last circuit. So how much you are taking the current source? So that current source will be delta I into delta Z. So that value you are compensating to maintain the voltage as well as the currents must be same. So to understand this, so we are going for the simple example. So before going to the example, the limitations and the applications must be similar to your Norton's and Thevenin's theorem only, because here also you are going for the entire network is replaced by a single voltage source in series with the single impedance. So now we are going for the one example. So the circuit carries with 4 ohms, 6 ohms, 3 ohms. with a voltage source of 10 volts. So suddenly the 3 ohms value, is changes with is adding with respect to 1 ohm. So how it will be the how how it will be the circuit deviations, and how we are compensating that. So that we are seeing in this problem. Okay, so from the circuit, so 3 ohms and 6 ohms, they are connected in parallel. And that must be connected in series with the 4 ohm resistor. So the total current I, can be represented as, so 10 divided by 4 plus 6 parallel with 3. So then the total current you are getting as 10 divided by 4 plus 2, or 1.6 amperes. So now the current flowing through 3 ohm resistor, by using current division, 1.67 divided by 6 uh, 6 1.67 into 6 divided by 6 plus 3. By using current division, total current into opposite resistance divided by sum of the resistance they are connected in parallel. So finally you can get the current flowing through 3 ohm resistor is 1.11 amperes. So now this current is multiplied by the change of impedance. So how much it is changing? 1 ohm is changing. So the source value of voltage, you have to take it as I into R, 1.11 into 1. So 1.11 volts you have to insert in the third branch with respect to this 1 ohm resistor. So this is the equivalent circuit. Like this you have to compensate the change in the parameters. So next, coming to the another example. So in this example, so we have to go for the compensation theorem, because the resistance R3 is increased to 30% of the circuit, 30% of the resistance value. So what is that resistance value? R3 is 20 ohms. So 30% is increasing. So how it will be, you have to see. Okay, so here 20 ohms and 20 ohms are connected in parallel in series with 5 ohm resistor. 20 into 20 divided by 20 plus 20, finally you can get 10 plus 5 is the total resistance value, and 75 is the total voltage value. 75 by 15, so you can get 5 amperes is the I1 current. So by using the current division, or you can simply say that the R2 resistance, R3 resistance, both are same. So automatically the total current is half of the value. So 5 amperes is the total current. So half of the value means 2.5 amperes. So that is the current flowing through 20 ohm resistor. Now this resistor R3 is increased to 30%. So 20 plus 0.3 into 20. So finally you can get 26 ohms. So what is the difference? Initially it is 20. Now it is changed to 26. What is the difference? 6 ohms is the difference value. So now the voltage is equal to minus I3 into delta R. So how much we are getting? Minus 2.5 into 6, that is equal to minus 15 volts. So this voltage you have to insert in the branch for addition of 6 ohms. So now this 5 ohms and this 20 ohms, they are connected in parallel. So 5 into 20 divided by 5 plus 20. So 100 divided by 25, you can get 4 amperes. 4 amperes plus 26 ohms. So 4 ohms plus 26 ohms. So 30 ohms. So total voltage is 15 volts. So now the total current is total voltage divided by total resistance. total voltage is 15, total resistance is 30, 15 by 30, you are getting 0.5 amperes. So once you are getting the 0.5 amperes, then you can go for the current division method. So you can go for the current division method. So by using current division method, so the current flowing through 5 ohm resistor is 0.5 into 20 divided by 20 plus 5. So finally you can get 0.4 amperes, and the current flowing through another 20 ohm resistor is how much? 0.1 ampere only. So net current is 0.5 and partially 0.4 amperes is flowing in the 5 ohm resistance, and final value is 0.1 value will flow in the 20 ohm resistor. So this is the equivalent circuit for the given circuit after increasing R3 resistance with 30%. So like this, you have to go for the compensation problems or Thevenin's problems or Norton's problems. Thank you.